Hi everybody! Let me demonstrate how you can create simple 2D shaders in Godot 4 and add them to your game background or UI elements. You will also learn a few things about the Godot shading language and how you can use it to build canvas item shaders. So, as you probably know, shaders belong to a unique category of programs designed to execute on GPUs. You can use them to control how the engine draws geometry and pixels on the screen, which allows you to build all sorts of effects. Let me show you how you can achieve one of these effects, and as usual, I'll try to explain every step I take. Okay, I prepared a simple 2D scene here. There is one child node in the scene and the node is sprite 2D, because we'll be working on a 2D shader of the type canvas item. I'm pretty sure that I saw this kind of shader somewhere on the web. I think it was on shadertoy.com, but the code wasn't documented at all, so I guess it could be useful to understand how it works, as you can utilize the knowledge to build your own variations of the shader. So the sprite has a simple black texture and I enlarged its region to the full size of the game window. What we need to do now is to create a shader resource and assign it to the sprite's material. Let's do it. So I'll just right click here to create new resource. Let's select shader, double click, and we need the mode canvas item. Let's call it, for example, I don't know, waves shader, and create. Now I will go here and open material of the sprite, create new shader material, click the material, and we'll drag our shader code here. Okay, let's double click the file here to open the shader editor. Alright, we are ready. Let's start with something simple. As you can see, Godot generated the standard function fragment, which is invoked for every pixel that belongs to this element. To set a color of these pixels, we will assign a new value to the built-in variable color. Let's just prepare it here. Okay, color is, and we'll add it briefly. So, color is a 4-dimensional vector, and it has the red, green, blue, and alpha components. And the values of these components are from the range from 0 to 1. For instance, I will make every pixel of the sprite red. Let's assign vector 4 and 1 for red, 0 for blue, 0 for green, and 1 for alpha to make it opaque. Let's see. Yes, everything is green now. I'll just zoom out so we can see the whole sprite. Very well, but this is a bit boring. I would like to modify the colors based on the pixel coordinates. Let's make use of another built-in variable, UV, which is basically coordinates of pixels of this sprite. So instead of just adding these constant values, we will change it to uv.x and uv.y. As you can see, the colors change only through a small square in the top left corner, because once the UV coordinates reached 1, the colors exceeded their max values. Let's see what happens if we add some kind of periodical function, for instance, modulo. So we will modify that by adding mod, and let's repeat it after a single unit. The first one, and modulo 1. Now the whole rectangle is filled with this pattern. We can make further enhancements to this simple approach, like combining both coordinates to generate all 3 components. Okay, so what can we do? We can, for instance, do this, like adding for y. Now we can here do a subtraction. And finally, what about to assign something to the green component? Let's do a multiplication and uv y. Okay. What if we want to zoom it in a little bit? Let me add another variable to keep the code readable. uv is a two-dimensional vector, so we need to assign it to vec2. Let's do vec2. Let's call it coords, like coordinates, is uv, and we'll zoom it by the factor of 10. And now, of course, we have to replace all occurrences of uv here by chords. 2, 3, 4, 5, and 6. There we go. Okay, I think it's now clear how Godot works with pixels in canvas item shaders. Let's delete the content of the fragment function and start over. This time, we will work with shades of gray, at least in the beginning. To get some more interesting values to play with, we will incorporate trigonometric functions, the sine and the cosine. So let me just write the first lines of this shader. Again, we will assign uv coordinates to this vector. Vec2 is uv. Vec2. Let's define another variable of the vector type to keep the values we need for the calculations. So it would be vector2, and let's start with just chords x and chords y. It would be, of course, possible to just put this parameter as a whole, because it would be automatically converted to vector2. But since we plan to do some more transformation within this function, let's keep it this way. And the outcome of this algorithm should be the color of the particular pixel. So let's define it. As we know, this is a four-dimensional vector, red, green, blue, and alpha. So let's call it color is vec4, and we will use the length of the vector we calculated in the previous lines. So it will be length and vector. Okay, and finally we need to assign the color to the internal variable color. Please note that shading language is case sensitive, so this is different from this. And unlike in Godot, it's necessary to end every line with a semicolon. Okay, so this is just the beginning. We can see some very small quarter of a circle here, because we are not applying the periodical functions yet. Let's fix it now. So instead of just coordinates, we will apply the sinus here. Okay, and cosinus. You can already observe some patterns there. What's wrong? Of course, one more bracket. There we go. And by the way, it's likely that with further calculations, the final value of the color could exceed the max value. So let's just implement a failsafe and do this. Color is, we use the method clamp, which means that the value would be kept within the given interval, in the given range, and 1. That's it. All right, So we have the basic pattern. Since the sine and cosine functions are periodic or cyclic, the pattern was automatically repeated across the canvas. But of course, we don't want to work with only shades of gray forever. It would be nice if the shader can be customized with the background color to mix with our calculations. Let's add the first uniform variable. We will do it here at the start, so uniform. This is basically the same as we use in the GD script with annotation export. So this kind of variables will show up in the inspector as shader parameters and can be modified directly there. Vec4 background, and now we will use this trick. If we assign it as a source color, this will automatically create a color picker in the inspector, so we can select our colors in a very convenient way. Vec4, and let's start with black, so everything would be set to 0. By the way, what happens if I use integer here? Nothing. Okay, seems to be fine. Nothing changed, of course. We only declared a variable, so if we just click the shader here, where it is, open it. No, of course not. We need to select it here in the material shader parameters. You already have background here with the color picker. But since we don't use it yet, no changes to this value would affect our pattern here. Very well, and let's add it to the final color value, plus background. Okay, what happens? Yeah, it was slightly modified, so we are on the right track. Very well, the effect is a bit darker now, but the pattern itself is a bit lame. Let me add more trigonometric transformations to calculate the brightness of the line segments. So we will start with adding a new variable, float. Let's call it bright, so it's not too long, and start at the top value. It will be in fact interesting to start at 1, then add fractions of calculated values, and finally subtract the rest from some other constant. Okay, here, and now we want to start with adding some more calculations here. So instead of assigning to a vector, we will just increase the value of coordinates. It looks strange because coordinates should be constant, but we will change it later. We'll introduce another variable. And instead of only using one trigonometric functions per the portion of the vector, let's use 2. So we will change it to cosinus and do plus sinus chords y, and similarly here we will start with sinus of chords x plus cosinus chords y. And of course we need to redefine vector because we don't have it there anymore. Vec2 vector is, and this is the second transformation I was talking about. We will create it by applying sinus of the changed coordinates, chords x, and cosinus chords y, and semicolon. How does it look now? Yeah, it was changed. It definitely looks better than the tilted squares before. Okay, and we want to use the length of the final vector to increase the brightness. Bright increased by length of the vector. Length of the vector. But this is in fact too big of a number. Instead, it would be more interesting if we use a reciprocal like this. Of course, it might be safer if we ensure that the vector length isn't a 0. Otherwise, we would get an error divided by 0. But we'll add this check later. Okay, we are not finished. We can, as I mentioned, we want to subtract this value from some higher value. So a higher constant, brightness, would be, let's say, 1.2 equals 1.2 minus brightness. You can, of course, experiment with this kind of values and to get some more interesting results. And finally, to apply that, we will add bright here. Let's wait. Yeah, it definitely changed. We are getting somewhere. Thanks to the usage of trigonometric functions and the brightness manipulation. Okay, let me just enlarge it a little bit so we can see the whole code. The pattern looks more interesting now, but there are other things we can do with that. Let's add one more sine and cosine calculation. So this will stay as it is, but now we will assign this value first to a temporary vector like this, and we will calculate the final vector as a combination of the previous two vectors. Let's do it. Vec equals vec2, and the parameters would be chords x divided by tmp x and chords y divided by tmp y. Okay, yeah, now we have a thinner, some kind of thinner lines, which is getting closer to the effect you could have observed at the beginning of this video. But it seems that the colors could be a little bit modified. Let's multiply that by, let's say, 0.5, which means it multiplies both parts of the vector. So this is just short for multiplying this part and then multiplying this part inside the brackets. Okay, let's try something smaller. Now, this is interesting. What if we add one more 0? Yeah, thin lines. Perfect. Okay, so let's give the lines some more variability to form something like waves in motion. And to do so, we want to repeat the calculation several times and add the iterations to the outcome. We'll make the number of iterations customizable as well, so it becomes our second uniform variable. Let's get back to the code and add, for instance, here, uniform integer iterations, and let's start with 3 iterations. Now, of course, we need to incorporate them into the fragment function. So let me right here, let me start with vec iter for iterations is vec2 chords. Why do we do that? The reason is that we don't want to manipulate the value of chords, because this should be constant. Instead, we want to reuse the current value of the particular iteration and iterate over that multiple times. What's wrong here? Vec iter, vec2 chords. Yeah, of course. The problem is that we need to define chords first. So the right place for this would be here. Okay, and now time to iterate. So let's create a cycle for int n starts at 0 and less than iterations, which is currently 3. So it would be 3 cycles, 0, 1, and 2. And in the shader language, yeah, something changed, because if we don't use curly brackets, the cycle is applied only to the first line, but we want to iterate over this whole block. So write this, and let's give it indentation to see the body of the cycle. Okay. Very well, but of course we don't see almost anything here, because the UV values are too low to have an impact on the result. Let's shift them a little bit. We'll add, for example, 250 here. See what happens. Nice. The effect starts showing an internal structure, which will be an important detail after we implement zooming in and out. But it would be better to allocate a new vector to store the current iteration values. In fact, we already did, but to use it at more places in these calculations. Let's do it here. Okay, blah, blah, blah. It's chords. Yes, of course. Iter is chords plus this. Now we're using it. This is interesting. We reached perfect squares. Why is that? Even if we tweak the parameter iterations, squares just stay here. Let me try it here. Yeah, 4, 5, 6. Still a pattern of squares. Because we forgot to use the new vector in the second calculation, and chords is now constant. Let's fix it. So first we need to change it here, because we want to calculate with the iterated value, and we need to change it here as well, right? Yes, the pattern is back. Okay, so the tangled web is back, but it's too dark. We want the lines to shine a little bit. Let's achieve that by normalizing the brightness value and increasing it exponentially to highlight the peak values. So let's get back to our function, and we will start by dividing the final value of the brightness by the number of iterations. Bright is, now we need of course to modify, make, what's the correct word, damn it, convert integer to float, otherwise it would show an error. All right, okay, now it's getting white, and it seems that we could do something about the color, increase the contrast between the light and dark areas. So let's exponentiate it to the power of 8. So vector color here, instead of vector bright, we will use the power function, here, power. It would be just safer to use an absolute value in case we get two negative values for some reason. So it's bright. Now the second parameter is 8 and end the bracket. All right, I like it. And of course, it would be nice to have it a little brighter than it is now. Let's change this value and again exponentiate it to the power of, let's say, 1.5. Power brightness and 1.5. That's nice. We're almost there. But the effect still looks like a pattern, and we would like to display something that at least looks a bit irregular. let's implement the zoom parameter. And just like before, we want the zoom to be customizable, so we'll add it as a third uniform variable. Uniform, it would be a float this time. Zoom is, and let's start at 5. Okay, and we will add one more uniform variable because we want to get rid of this constant. That should be, it works like something like a light power or intensity, so it would be great to have it here in the shader parameters as well. Let's do it now, float and call it power, and it would be 0.5, because if we keep it as 0.005, it would be pretty difficult to use this slider to set some other values. So we will just use it as a multiplicator and multiply it by 100 in the code. Okay, so that's all about the uniform variables for now, and let's do the code. First, let's calculate the intensity. Intensity is power multiplied by, okay, not 100 but 100ths, and now we want to divide these coordinates by the zoom factor. Let's wait for it. There it is. Very nice. So the tangled wave is here, but something important is still missing. Yes, exactly, it's not moving. Let's implement a motion using another built-in variable, time. So what we need to do is to get back to the script and define the time. That would be dependent on the, which one? 5th uniform variable called the speed. So we'll be able to dynamically modify the speed of the effect motion. Float speed would be 0.1. All right, and I think that's the final uniform variable we won't use anymore. And now let's calculate it. Float time is the internal time. Basically, it's time elapsed from the start of the shader calculation and speed. And of course, now we need to use the time. Let's add it to both trigonometric calculations. So we will start here and do this time minus iter x. Okay, it's already moving, but that's not everything. We want to make it a little more unpredictable, so we will combine adding and subtracting at all these arguments of these trigonometric functions. And again, sinus time plus iter, or maybe minus, might be better here, and it actually doesn't matter. You can change these signs as you want to, and the effect will be pretty the same, but for some reason I found it interesting to just switch between them from time to time. And finally we'll do it here at the temporary vector calculation, time plus iter x, time plus iter y. All right. So we reached our destination. Let's try to modify the shader parameters. For example, we can increase iterations so it becomes brighter. We can change the zoom, zoom out, zoom in. Let's just decrease the power so it's not so bright, and probably iteration should be decreased as well. And of course, it can run at a faster speed. This is pretty cool. And what if we don't want to have just a black background? Let's try, for example, some kind of green. Very cool. Or orange, anything. Just use the color picker and do your experiments. And of course, you are free to add more complicated functions to give the lines even stranger shapes and movements. So I will just return to the original values. And that's all. Thanks for watching. I hope you found the Godot shaders at least as interesting as I did. And next time I might try working on something more sophisticated. For instance, a shader that rates and manipulates the underlying texture. See you in the next video.